Okay, hi folks. So in this video I'm going to be going over IB Physics Standard Level November 2019 Paper 1. As you know, the Standard Level Paper 1 exams, they contain 30 marks, and here we have 30 MCQs distributed among the different topics in this way. I made a small mistake here. I'm going to just change topic 1 to having 2 questions and topic 2 to having 6 questions, as you'll see in a minute. But yeah, let's just get started. So we're going to jump to the first question, and the first question is about derived units. So we have to see which quantity has the fundamental SI units of that. So what we have to do there is simply just know our definitions. You need to know what joule is. It's 1 Newton meter. You need to know that a Newton is 1 kilogram times 1 meters per second squared. And knowing those things, you just have to work them out and express all these quantities in fundamental SI units. And in the end, you'll see that it's pressure that works. You're going to get meters times meters to the -2, giving you the meter to the -1 that you need. So that's a question on derived units. Okay, then question 2. This is really a question about the equilibrium of forces, right? So it's kind of vector addition. That's why I've decided to sort of categorize this as a topic 1 question. We're dealing with vectors here, but of course it's also topic 2 in the sense that you need to know that if an object is in equilibrium, then the net force adds to 0. So, and here we have to sort of balance out all these forces. We are given 3 equations, and you can see the first equation really relates the horizontal component of F to G. So you can see, okay, if we project F horizontally down, then we get F cosine theta, and that component of F has to balance out G. So the first equation has to hold if these forces are in equilibrium. Of course, the vertical component of F has to also then balance out H, but that's not there. Okay, then the second equation, you can see F has to equal to some components of G and H. So what we're going to do there is draw a line parallel to F, draw a line along F. And then we're going to look at, first identify some angles. We have theta there, vertical angles. The projection of G onto that line parallel to F is G cosine theta. And then we also have to project H onto that line. And we do a little bit of trig, identify theta down there. And then it's H sine theta. That is the component of H along that direction. And those 2 forces added up, so G cosine theta plus H sine theta has to balance out F. They're all pointing along the same direction, and since they're in equilibrium, then they need to balance out. So the second equation is also true. Now the third equation is of course not true because F, G, and H are magnitudes, and of course the magnitudes don't add up in this way. So yeah, it's only. So the correct answer is A, 1 and 2 only. And that's, I would say it's a topic 1 question, kind of topic 2 as well, where we are doing vector addition. Yeah, I just wanted to go up and write that the first question is on derived units, and this question is on 2D vector addition. Okay, next question. Yeah, and this is where by the way, I reclassify those 2 questions as topic 1 questions, and there are going to be 6 questions in topic 2 as we see. So yeah, so now we start topic 2 questions. So this question is about this is a terminal velocity question. We have a constant force pointing to the right. We have a varying force that is proportional to velocity going to the left. So that sort of increases as the constant force accelerates the object to the right. So it definitely doesn't start off with 0 acceleration, because if there's no varying force and only the constant force, then it's going to accelerate to the right. So it's not A or B. And the velocity is going to start increasing, but it will reach a maximum because as the varying force increases with increasing velocity, then it's going to eventually have the same magnitude as the constant force, and then there's equilibrium, zero net force, zero acceleration, so it's going to just continue moving with that maximum terminal velocity, and that velocity is not going to start decreasing, so it is only c. That's correct. So that's terminal velocity. Okay, next question is a graph. We have an acceleration versus time graph. So we just need to remember that the area, well, first of all, yeah, they're asking for the change in velocity delta V, and we have to remember that change in velocity delta V is the area under an acceleration versus time graph. You know, acceleration times time has units of meters per second, so that's velocity. So yeah, so we just need to find the area. We clearly see we have an area of 2 there, and then okay, trapezoid. Use the trapezoid formula if you want to, or just divide it up into a triangle and a rectangle. I just like the trapezoid formula. You get it sort of in one go. So that's half times the height times the sum of the two bases, parallel sides. So yeah, you get 2, 8, and 10 in total. Okay, next question. Climber sliding down a vertical rope has an acceleration. What's the average frictional force? Okay, so free body diagram. So we're going to first draw the weight, of course, mg, and then there is a friction force pointing upwards. It's going to be a little bit smaller because he is moving down, sliding down with an acceleration a. So there is a net force down, but F is pointing up a little bit. And then let's write down Newton's second law, that mg minus F, the net force, equals to m times the acceleration. So that's just Newton's second law. And then we just rearrange to get F like this, and then we can see C is the right answer. So that's an F equals MA question, which I'm going to write in a minute, I think. Yeah. Okay, now question 6 is a cube sliding down the surface. Constant velocity, key point, right? So net force is 0. So the frictional force that is pointing up the slope as it's sliding down has to balance out the component of the weight parallel to the slope, right? So just to maybe remind you, in case you forgot, we can sort of label the angle, and we know mg is pointing down, and then we know the angle is also up there, and then mg sine theta is the component down the slope, parallel to the slope, and that has to be equal to the friction force pointing upwards because it's moving with a constant velocity. So that's that. And that's really sort of a friction question, I would say. But it's also, of course, vectors and mechanics. Okay, question 7. Yeah, kinetic energy is half mv squared. And we know thrown up vertically, no air resistance. We know the velocity is just changing according to the Suvat equation, minus at plus u. And then, of course, we can expand that. You get a nice quadratic equation with a positive quadratic coefficient. So it's a parabola opening upwards. And that's D. That's the correct answer. So parabola opening upwards, facing, I should have said opening upwards. Okay, now I'm just going to label questions F equals MA. And 6 is friction question. And this is a kinetic energy question, say. Okay, moving on. Okay, we've moved on to topic 3 now. So that's nice. No, sorry, we're not. Still in topic 2. Sorry, elastic potential energy. And okay, so we know elastic potential energy. I sometimes like to write that as EPE is half k x squared. So proportional to the displacement squared. Now, if we're looking at a displacement that is quarter of x, then the potential energy is going to be 1/16 of the energy when it's stretched to x. Okay, so you can write that the second elastic potential energy is 1/16 of the first potential energy. That means, of course, that the change in elastic potential energy has been 15/16 EPE, and that is energy that has been lost in the spring, so it's work done by the spring on the surroundings, and that is D, is the answer. So this is an elastic energy question. Okay, now we are done with topic 2 finally, and we get to topic 3, and we get to do some calorimetry here. Water and ice cubes mixed up, and we just have to look at the energy flows carefully. So read the question carefully. We have water that's at 290 Kelvin, then ice is at its melting point, 0 degrees Celsius, 273 Kelvin. We want to reduce the water temperature to the same temperature. So the water was 290 to begin with, and we want to reduce it to 273. So it has to lose some energy, right? And the temperature change is 17 Kelvin for the water. So we're going to use the MC delta T equation to express the energy that the water has to lose and give to the ice that is melting. And we know that the energy that goes to melting a certain amount of ice is M prime L, L the latent heat of fusion. So the minimum mass of ice is the M prime we can isolate, and we get MC17/L, which is A. And that's a calorimetry question. Okay. Question 10 is ideal gas, an ideal gas law equation, and pretty straightforward. We have to sort of look at how does the pressure change with volume and temperature. So just write down the equation. P equals nRT/V, and we can see if we want P to decrease, T has to decrease, the temperature decreases, or V could increase. So yeah, D is the correct answer.